Hiya folks, welcome to another video on physics required practicals. This one is from the forces topic and it's about the extension of a spring. And the purpose of the investigation is to find out what the effect of changing the force applied to a spring is on that spring's extension. At the end of it, with your data, you'll then calculate the spring constant of the spring. Now I know that's a term that usually causes a bit of confusion, the spring constant, and we can simplify it by just saying how stretchy a spring is. That's what the spring constant is. Okay, so you can see I've got a spring set up here, and you can see that's quite easy to stretch. Okay, I'm applying a very small force there. That's actually 1 Newton of force. But if I apply that to there, you can see that the spring actually stretches a fair bit with even a small force applied. But if I got a spring with a really high spring constant, like let's say a suspension coil from a car, obviously that's got to cope with way more weight than this spring will. So its spring constant is much higher. So the spring constant of that spring, if I was to hook this up here and put 1 Newton on it, you wouldn't even see the spring stretch at all. So we can calculate that though from the results that we get throughout this investigation. Okay, so this is Hooke's law, and at the top there you can see it says F equals K times E, and I've written underneath what each one of those means, but you should have done Hooke's law anyway during the forces topic. But force is equal to spring constant multiplied by extension. Now we're not interested in calculating force, we know what the forces of these are. We know that gravity on Earth is 10 newtons for every kilogram. Now, I don't know if you can see, I'll pick one of these up. On the mass there, it says 100 grams. So if it's 10 newtons for every kilogram, and 100 grams is a tenth of a kilogram, then this isn't 10 newtons, it's 1 Newton. So every one of these is going to be 1 Newton applied to it. So I know what the force is, so I don't want this equation. I want to know what the spring constant is, and if you rearrange it, the spring constant is equal to the force divided by the extension. So my investigation is now based around this rearranged equation, this Hooke's law equation, to find the spring constant of that spring. Okay? How am I going to know what the force is? Each one of these is 1 Newton. So every time I add one, I know what the force is going to be. That's 1 Newton in a minute. If I've got 2, I've now got 2 newtons, and I can apply those to the spring. The extension is what you're going to be measuring throughout the practical. Okay? So I'm going to start off with a spring unstretched. Now this spring on the clamp, I'm going to measure it now with a ruler, and I'm going to find out what its unstretched length is. Okay, so if I hold this ruler up, I've actually already measured this, but just to show you what I mean, if I hold the ruler up there, what I'm going to do is I'm going to measure not the curls at the top of the spring, not the round bit at the top and the bottom. I'm going to measure the body of the spring, and I'm going to make sure I am consistent measuring the exact same thing every time. What do I mean by the body of the spring? I'll just show you with a quick diagram. So I'm not sure how much detail you can see of that spring that's just kind of hanging there, but there's a loop at the top, and then there's the main body of the spring that looks like that, and then there's another loop at the bottom. And what I'm going to do is I'm just going to measure from there to there throughout the entire investigation. I'm not going to measure these two at the top and at the bottom, because as I apply mass to those will very slightly start to curl out and stretch. That's going to affect my results. It's going to be way more accurate if I just measure this portion every single time. Okay, consistency with your results will increase the accuracy of your results as well. Okay, so I'm going to measure that, and I just hold the ruler up next to that, and you can't see on there, but that's 2.1 centimeters. Okay, so I've got the student sheet for the required practical printed out here. It will be on your screen at some point during this video, because I'm going to give you the data and you can process it yourself, and you can investigate the spring constant of this spring, even though you've technically not done the practical yourself. I've done it for you. Well, you will have done it in lessons anyway. Okay, so at the back of this, you can see there's a results table there, and I've already written in the first couple of data points. Okay, so it says here, when the weight was 0, well, there's no weight currently on it. The length of the spring was 2.1 centimeters. That's accurate. I've just checked that with a ruler. It's currently 2.1 centimeters, and the extension of the spring is 0. Now, how did I get to that, the extension of the spring? Well, to calculate extension, I need to know, 1, what the length of the spring was to start with nothing on it, and 2, after you've applied a force, what's the new length? Because with those two pieces of data, if I subtract the starting length with no force on it, 2.1 centimeters, from the end length, which is going to be after I've applied a force to it for the rest of this investigation, if I subtract the start length from the end length, it'll tell me how much it's changed by. So that's going to be this extension of the spring. The extension of the spring. So that's where that number's going to plug in later on, and we can work out what the spring constant of this spring is using that data. Okay? So you might be asking then, well, why is the extension currently 0? Well, I've just told you it's the start length minus the end length. The starting length of this I've just measured is 2.1. I've applied my 0 newtons of force. Basically, I've not put a force on it. and the end length is 2.1. So what's 2.1 minus 2.1? It's 0. There is no extension currently because there's no force applied to it. Remember, Hooke's law states the extension of a spring is proportional to the force applied to it. Okay, so let's start the investigation then. I'm going to add this mass hanger with a mass on the bottom. I just want to point something out. I've been asked this a few times in lessons, but you might already know the answer. If you look at that, it says 100 grams on it there. And if you look at these masses, they also say 100 grams on it, that's fine. But then if you put them side by side, you'll notice that this one is thicker than this one. And that's because this one has been altered to take into account the hanger as well. That adds to the mass of this. So even though that doesn't look like it's going to be 100 grams, the whole thing together is 100 grams. Okay, so I'm going to add this to this. I'm going to do it slowly because I don't want it bouncing up and down whilst I measure it. Okay, give that a second to settle. And I'm going to use a ruler to measure the new length. Okay, so if I set the new ruler up next to it and I have a look at what the new length is, I'm going to measure in exactly the same way I did earlier. So from the top of the spring to the bottom of it, and that is currently 6.1 centimetres. Okay, so on my worksheet now, as if it was your worksheet, I would write down the weight was 1 Newton because I've applied 1 Newton of force to it. The length of the spring is now 6.1 centimetres. 6.1 centimetres, and then the extension, remember, is just the length of the spring, the final length of the spring after you've applied the force, minus the unstretched length, the starting length, which was 2.1. So what's 6.1 minus 2.1 is 4, isn't it? So the extension of the spring is 4 centimetres. So I'm going to keep applying masses to this now, and I'm going to keep updating my results table, and I'm going to keep calculating the extension. I'm actually going to save the extension calculations for later on. I'm just going to get the new length data all the way down, and then I can calculate extension later on, okay? So let's add another mass to this. I'm going to slowly let go of that. Okay, let that settle. Get my ruler. And measure from exactly the same point as last time. And that's currently 11 centimetres. Okay, so when the force was 2 newtons, the length of the spring was 11 centimetres. Let's keep going. I'm going to add another force to it. I'm going to support this with a hand. I'm going to let go of that. And we'll let that settle. Measure from the same point as last time. That's currently 15.5 centimetres. So 3 newtons of force, 15.5 centimetres. Now I want to pause at this stage and I want to discuss some of the other pieces of equipment that you've probably seen. Okay, this down here is a clamp, and the clamp's there because as I keep adding masses to this, it would get to the point, if that clamp wasn't there, when this whole thing would tip over. Now that's a safety concern. It's also something you might need to mention during like a 6-mark question or a question regarding any practical about what safety precautions would you need to take. So the biggest concern here is, one, that tipping over, landing on someone's foot or hitting someone. If you get 10 of these and drop them on someone's toe from this height, you could definitely break a toe. Okay, so we want to try and avoid that by clamping it to the desk. But also, just for safety, even though this is clamped to the desk, what happens if the spring was to snap? So I'm not going to stand there with my feet underneath the clamp, not the clamp, sorry, the spring, because if it dropped, well, it'd do some damage, okay? The other thing is goggles. So you should be shouting at the screen now that I should have goggles on, and you're right, I should have some goggles on, okay? If this spring was to slip off here, it could ping off and go who knows where. Also, there's a kind of an alternative method to this practical, where you don't just apply like 10 newtons of force, you just keep going. And you keep going until the spring ends up, well, being destroyed, basically. The spring gets extended beyond its limit of proportionality, beyond its elastic limit, and it no longer returns to its original shape, which means it stretches that much that it usually pings off and the masses all hit the floor and it makes a big bang. So we should be wearing a pair of goggles for that. What I will say is, though, it's secured in the clamp at the top there, and I know that these amount of masses aren't going to cause that to happen, okay? So I'm not testing this one to destruction. I'm going to stop before then. I just want enough to be able to calculate the spring constant, okay? So I'm going to keep going now. I'm going to add another mass on here. I'm going to let that drop. Okay, and I'm going to measure it from exactly the same point, same as I did last time. And we're now at 20 centimetres of extension. Okay, so when the force was 4 newtons, I just said extension when it should have said length. The length of the spring was 20 centimetres. Okay, let's go again, add another mass. Okay, measure from the same point again. We're now at 25 centimetres, so when it was 5 newtons, it was 25 centimetres. And I'm going to do one more. That should be enough data at that point. I've got 6 results. Okay, I'm going to measure. Same spot again. And that is 29.5. So when it was 6 newtons of force, it was 29.5 centimetres in length. So I'm going to stop there. I'm going to calculate these extensions, and then I'm going to show you what you're going to do with this data, how you're going to process it to calculate the spring constant of the spring. Okay, so here's my results. You can see them there. I've calculated the extension of the spring for all of the forces applied, and these are the forces applied. So as I applied 1 newton of force, I got 4 centimetres of extension. As I applied 2 centimetres of force, I got 8.9 centimetres of extension. You can see what the relationship is between those two, okay? Now, I'm actually going to ignore this section here, so the task that it's got for me there. I'm going to switch to this one, because I think this one does a much better job of explaining what it is that you're trying to calculate and what the relationship is between the variables that you've investigated, okay? So we've actually done all of this section now, okay? So we've done the method, we've recorded our data, we're now down to the analysis stage, okay? So step 1 on the analysis stage says to plot a graph of force in newtons on the y-axis and extension in centimetres on the x-axis. Now, you might think, hang on, why are we doing it that way around? Because in science, you've been told that the independent variable is a thing that we're always going to put on the x-axis. So the factor that you change goes on the x-axis. Well, we're doing this on purpose. This isn't a mistake. We're doing it on purpose. I'm going to show you why in a second, okay? We then need to draw a straight line of best fit on your graph. So we're going to see the relationship between the two variables. You're going to see that there is a proportional relationship between them. We're going to draw a straight line, okay? It then says calculate the gradient of the line of best fit. Now, why would we want to calculate a gradient of this when we know that to calculate the spring constant of the spring that we've just tested, we could just do the force divided by the extension? Well, if we use the gradient on a graph, which I'm going to show you what it's going to do in a second, if we use that gradient, it's going to be more accurate because it's taking all of our data at once and using that to calculate the spring constant. Well, how is that possible? Well, if you look at this, I'll show you the top part first. Okay, so this is, it's not for our set of data, this is from a different set of data that I've collected from somewhere else. You can see that the force has been put on the y-axis, like we were asked to do in the analysis section. So the force is on the y-axis and the extension is on the x-axis. And you can see here there is an obvious relationship, they're proportional, between the force applied and the extension. Okay, so why does it want you to do it that way around, and why we're calculating a gradient? We've discussed that calculating a gradient is going to be more accurate, but the reason for that is this. You've done in maths and you've done in science, you've been told that the gradient is equal to the change in y divided by the change in x. Now, if you look at that now then, so the change in y, what's on my y-axis? It's force. So we're actually doing the force, or the change in force, divided by the change in extension. What does that equal? Look at that. The spring constant is equal to the force divided by the extension. So that's going to tell me the spring constant. If I work out the gradient of this graph with our data, we're going to get the spring constant of that spring. And it's going to increase the accuracy of our result, because we're taking into account all the results at once when we're using this to calculate the spring constant. Okay, so it said to draw a straight line, and that's perfect, but what's gone on here? So you can look, you can see on this data, there's a couple of points that quite clearly don't belong to this nice straight line here. So what happened at that point? Well, actually, it's something around here that's happened. Okay, so if I show you the other graph on the other side of this page, you can see that there's a secondary curved line that's been drawn on there. Okay, now you probably were told about this during your forces lesson on this, but around there is something that we call the limit of proportionality, which sounds fancy, doesn't it? What does that mean? Proportionality, right. So what that actually means is that it was proportional up until this point, and after that point it stopped behaving in a proportional manner, meaning that up until that point, every time I added a force, I got a certain amount of extension, and when I doubled that force, I doubled the extension. But then that didn't happen over here. It took a relatively small amount of force after 6 newtons to cause the extension to get quite long. Okay, so that there is what we call the limit of proportionality, and eventually we would reach a point where the spring would break. Okay, but that's not what we're interested in. We're literally interested in this part and calculating what the spring constant of our spring was. Okay, so these were just demonstration graphs. You don't need to do anything with those graphs, but I do want you to try. Excuse me. I do want you to try and calculate the gradient of this graph. Okay, so if you've got graph paper at home, that's great. You can try that. If you've not got graph paper at home, then you could use Excel to make a graph. There's graph makers online as well. Just give them a Google graph maker, stick your data in, and it's going to be weight, and that's got to be on the y-axis, and it's going to be extension, and that's going to be on the x-axis. If you then calculate the gradient of the graph that you produce, you should be able to work out what the spring constant of your spring is. Okay, so we will have done that, and that. It then says the gradient in this line is therefore equal to the spring constant. What is the value of the spring constant in your experiment? You'll have done that because you've calculated the gradient. Okay, so this last one, it says what will be the unit for the spring constant. If you're not sure what the unit should be, then you need to look back at your equation and work it out, okay? It's not going to be something random. It's going to be something based on the information that you already know. So if you look at this, force, we know force is measured in newtons. Extension, now we currently measured, for this experiment, the extension in centimetres, okay? So we're going to use centimetres, but don't be surprised if in an exam situation they're asking for it in metres, okay? We can convert this into metres if we need to as well. That's absolutely fine, okay? But in this case then, it's force, which was in newtons, divided by extension in centimetres. Newtons divided by centimetres. Oh, look at that. There's our unit. It's newtons per centimetre. So when I said right at the start of the video that the spring constant of a spring is how easy it is to stretch, you can kind of understand why now, because the bigger this number is, the more force you need to cause a certain amount of extension. Okay, so you should find that the spring constant of the spring that we've just tested should be fairly small because, well, even by applying 1 Newton of force, we got a fair amount of extension out of it, didn't we? Okay, so that is the investigation in a nutshell, basically. That's all you needed to do. Apply a force, measure the length, calculate the extension, and then graph it, and then use the gradient to work out what the spring constant is. Okay, if you've got any questions, just stick them below on the YouTube video, or you could email them to me, and yeah, hope that helps.